Hey folks, welcome to another set of Chemistry 2 video notes. Today we'll cover the first half of Chapter 8, which teaches us the basics about chemical reactions. We'll learn what a chemical reaction is, how reactants turn into products, how to balance equations, and how to recognize what type of reaction we have based on the chemical equation. Let's get started. If you'll remember back to when we talked about physical and chemical changes way back in Chapter 1, you may recall that in a physical change, we end up with the same substance that we started with, just in a different form. In a chemical change, however, the reactants come together to form new substances that have a different chemical makeup and different chemical and physical properties. This is the same story here, but we're going to dig a little deeper into what those chemical reactions look like. Let's say we put into a flask some colorless insoluble gas such as hydrogen, and along with it a purple also insoluble gas such as iodine. These two gases will react together to form hydrogen iodide, which is a gas that is colorless, highly pungent, and readily dissolvable in water. This is an example of a chemical reaction. We took two substances with their own set of chemical and physical properties and produced a new substance with a different chemical formula and different properties. This particular reaction, and others that only involve gaseous reactants, is considered a gas phase reaction because it takes place in the gas phase. You probably very easily recognize that this is a chemical reaction, but you might be wondering, why would this even occur? What could possibly make our H2 and I2 molecules break their very strong covalent bonds and form new ones? Well, hey, that's a great question, and I'm very proud of you for thinking that deep into this. For your excellence in curiosity, your reward is an answer to that question. Remember how we talked about gas molecules moving very quickly, to the tune of hundreds of miles per hour, even at room temperature? Moving that quickly, when those molecules run into each other, there's bound to be something amazing happen. Think about when two vehicles crash together at high speeds. Glass breaks, metal bends, tires fly off. There's a whole lot of energy being transferred within that collision. The kinetic energy of those vehicles is enough to break them, just like the kinetic energy of our molecules is enough to break their bonds. It always requires energy to break a chemical bond, no exceptions. The opposite of that is also true. When we form new bonds, we always release energy. Now, the difference between our car crash analogy and our molecules is that our molecules can form new bonds and create new substances, but our cars just stay broken. So in this case, our H2 molecule runs into an I2 molecule, and the kinetic energy breaks the bonds. The hydrogen atoms form new bonds with the iodine atoms, creating two molecules of HI. Of course, reactions are usually a bit more messy and complicated than this and involve a lot more molecules, but for now, this simplistic view of how chemical reactions take place will suffice. Take special note of our particle diagrams here. We started with 2 atoms of hydrogen and 2 atoms of iodine in our reactants, and we still had 2 atoms of each in our products. This is very important and leads us into our next section about balancing equations. One way you could read this equation is 1 molecule of diatomic hydrogen reacts with 1 molecule of diatomic iodine to give us 2 molecules of hydrogen iodide. You might also just say hydrogen reacts with iodine to produce hydrogen iodide. The first way makes it very clear what this reaction looks like. The second way might lead you to write your chemical reaction like this. That would be incorrect, though, because we're lacking 1 atom of hydrogen and 1 atom of iodine on the product side. This equation would not be balanced. To show the balanced equation, you need to specify that there are 2 molecules of HI for every 1 molecule of H2 and I2 that react. Notice all we did was add a big 2 in front of the HI. That big 2 is called a coefficient, and it tells us how many molecules of HI are in this reaction. H2 and I2 also have coefficients, which we assume to be 1 since they're not written in. So why did we just add a molecule of HI instead of changing HI to H2I2? Wouldn't that balance the equation as well? Well, technically, yeah, but remember, our substances are dependent on what they're made of. A molecule with 1 atom of hydrogen and 1 atom of iodine would be significantly different than the hypothetical and completely impossible molecule made up of 2 atoms of hydrogen and 2 atoms of iodine. So if you want to balance your equation, which you need to do so our reactions are appropriately expressed and follow the law of conservation of matter, you simply count up how many atoms of each element you have on each side of your equation. Figure out if any of those elements are not balanced, Add a coefficient where you need to, recount your atoms, and keep adding coefficients and recounting until all of your elements are balanced. And remember, we never, ever, ever, ever change subscripts, because that would change what substance we're talking about. Let's do some examples. I promise we'll try some new equations, but what if I got this one to balance as 2H2 plus 2I2 gives us 4HI? Would that be wrong? Absolutely not. The particles are still balanced on both sides, and it's just a multiple of our original equation. So when it comes to the math in Chapter 9, it will all still work out the same. Chemists tend to simplify our equations, though, and use the simplest whole number coefficients that we can. So let's try to balance an equation. If we're told that nitrogen reacts with hydrogen to give us ammonia, we might start our equation out like this. When we count up our atoms, we'll see that we have 2 atoms each of nitrogen and hydrogen in the reactants, but only 1 atom of nitrogen and 3 whole atoms of hydrogen in the products. This is currently an unbalanced and incorrect equation. The order you do this is completely arbitrary. You could choose to balance either the N's or the H's first. Either way works. I'm going to go with the N's because they're the first element I wrote down. I need more nitrogens on the product side, so I'm going to put a 2 in front of the NH3. This gives me now 2 atoms of nitrogen, which balances out my N's, but I have 6 atoms of hydrogen now. So my hydrogens are still unbalanced, and I need more on the reactant side. If I put a 2 in front of H2, that gives us 4 atoms of hydrogen, which still isn't quite enough to get to 6, so I'm going to put a 3 there. This gives me 6 atoms of hydrogen on both sides, and now I'm all balanced. Let's do another example. Let's do methane plus oxygen gives us carbon dioxide and water. A helpful hint when balancing, even though your order is completely up to you, it's sometimes easier to save any pure elemental substance for last. So in this example, I'm going to hold off on balancing my oxygens until very last, since I can put a coefficient in front of O2 and it only affects how many oxygens I have and no other elements. I've got 1 carbon, 4 hydrogens, and 2 oxygens on the left, and 1 carbon, 2 hydrogens, and 3 oxygens on the right. The first thing I notice is that my hydrogens are not balanced. If I put a 2 in front of H2O, that gives me 4 hydrogens now and 4 total oxygens. Now the only thing left is to fix my oxygens, which is a pretty easy fix. I'll just put a 2 in front of the O2 and now I'm all balanced. Let's do one more example, this one a bit trickier than you've seen so far. If I tried to balance the equation for the combustion of octane, a couple steps in and I'd probably be about here. At this point, I know that I need more carbons on the right, so I'm going to put an 8 in front of CO2. This gives me 8 carbons on both sides, and now 17 oxygens on the right. Next, I'll balance my hydrogens by putting a 9 in front of H2O. This gives me 18 hydrogens on both sides, and I've still got 2 oxygens on the left, but now I have 25 oxygens on the right. When you get to this point, it's probably a little frustrating because there doesn't seem to be a clear path to victory. The only thing I can do is multiply my O2 by 25 halves, which would give me 25 oxygens on the left. But can our coefficients be a fraction? Well, technically, yeah, they can. It's still balanced and mathematically reflects what's happening. But we're not going to have half of an oxygen molecule floating around. So it's common practice to take this fractionally balanced equation and multiply all of the coefficients by a number which would get rid of our fraction. In this case, 2. So our final answer will have coefficients of 2, 25, 16, and 18. So for balancing equations, my best advice to you is 1. Never forget that we're talking about actual particles, and sometimes it's best to even draw the particle diagrams to help us understand what the equations say. 2. Don't forget to recount after you add a coefficient. And 3. If you have pure elements in your equation, try to save them to balance last. Other than that, the whole process is basically trial and error. It'll take you plenty of practice until you get the hang of it and start to easily recognize the quickest ways to get our equations balanced. Last up on our list to talk about today is the types of reactions. If you'll think back to biology class, we classify living organisms under different categories. There are 3 domains that cover all living organisms. In just the domain eukarya, you've got 4 kingdoms. Within each kingdom are multiple phylums, then classes, then orders, families, genuses, and species. This helps biologists organize organisms so they can compare them by their traits and understand them better. Chemists do something similar, but without all of the King Philips coming over from Great Spain. Over the years, chemists studied hundreds of thousands of seemingly unrelated reactions and have realized that we're having trouble comparing them without some sort of organizational system like the biologists have. Ours still isn't quite as impressive, but there are 4 basic categories of reactions that help us to organize our knowledge a little bit better. Single replacement reactions are when one element replaces another in a compound. Think of it like when you and your friend are tossing a ball around. When you pass the ball to your friend, that's like a single replacement reaction, the ball being the element that's doing the replacing. This illustration here is another simple way to think about it. The green box leaves the blue box and joins with the red. A double replacement reaction would be like if you were holding a ball and your friend was holding a frisbee, and you threw them to each other at the same time. A little more complicated, but basically two compounds will swap some of their stuff with each other and form new compounds. In this picture, the green and red parts stay the same, but they swap the blue and purple parts. One way I like to remember the difference between these two is that a single replacement reaction both starts and ends with an element and a compound. A double replacement reaction usually starts and ends with two compounds. Decomposition reactions are basically when a compound breaks apart or decomposes into smaller substances. That's like when you and your friend break up, so to speak. And a combination reaction is just the opposite. Almost all reactions can be classified as one of these four. There are other classifications though, and many reactions can be classified as more than one type of reaction. For example, let's think about our example before with methane reacting with oxygen to form carbon dioxide and water. This is probably best described as a double replacement reaction because the carbon in methane gives some of its hydrogens to oxygen, and the O2 gives some of its oxygen atoms to carbon. This is also considered a combustion reaction. A combustion reaction is any time a substance reacts with oxygen. In the case of hydrocarbons like methane, they're double replacement reactions and always produce CO2 and H2O. We can also combust metals like iron to form metal oxides. The equation for iron's combustion looks like this. Is that a double replacement reaction? Well, no, that's two substances coming together to form one. So it's a combination or synthesis reaction. We'll learn about a few other types of reactions as well, but for now you need to be able to recognize these types, so let's do some examples. Our first example is the reaction between calcium ions and carbonate ions forming solid calcium carbonate. Notice the state symbol AQ here. This stands for aqueous and means the ions are dissolved in water. Calcium carbonate is a solid here, but if it were labeled as aqueous, you'd assume the calcium and carbonate ions were separated just like they are in the reactants. Anyway, you can easily recognize that we have two reactants and one product, so we have two substances coming together to form one. That's a combination reaction. What about the reaction of aluminum powder and rust, or iron 3 oxide? This is called the thermite reaction. We start with elemental aluminum and a compound and end up with a different compound and the elemental iron. That's a single replacement reaction. The ball being passed between aluminum and iron in this case is the oxygens. Next up, let's try the heating of mercury 2 oxide to produce liquid mercury and oxygen gas. This is one substance splitting up into two simpler substances, so it's a decomposition reaction. Lastly, let's try phosphorus trichloride and silver fluoride producing phosphorus trifluoride and silver chloride. We start with two compounds and end up with two compounds, so you might assume this is a double replacement reaction. If you did, you'd be correct. In this case, the phosphorus and silver swap their halogen counterparts and form two new compounds. Well, have you had enough for today? Think we should call it here? Me too. That's all I've got for you in this set of notes. Tune in next time for the rest of Chapter 8, which is some pretty new stuff for you, so get ready. As always, if you have any questions, please ask.